Okay, so welcome to the makeup lecture. So I'm going to take a break after about 90 minutes, and then we'll have another hour after that. I have the midterms that I will distribute during the break. Yeah, I mean, assignment 1, you should have received your feedback. Basically, on question 1, some marks were up to 5 marks were deducted for not including testing, but I guess the handout was not clear that you needed to submit testing. So basically, everybody will get 5 more marks to the marks that were indicated in the feedback. This will be your corrected mark for that assignment. And then the test grade, I posted them yesterday, and they were, the average was kind of lower than, I would like, and so I increased, the marks will be increased by 8 marks out of 75 to what has been posted on the website when I calculate the final grade. Okay. Any questions? Okay, so basically what I'm going to do today is, finish the heuristic search part of the course. The lecture slides for this are already posted, and the assignment should be coming out, assignment 2, later today, and it's basically on heuristic search. And so for modeling a problem and then running some search algorithm that we provide on this problem, this is in Prolog. So basically, you will see when the assignment is posted. Okay, so let me go to the Yeah, so last time we had seen some basic algorithms for doing heuristic search, including A star, which is probably the key heuristic search algorithm. And we started looking at properties of heuristics that would, give us some guarantees about how that the search will produce, will have the right property, will produce the right result. So we saw 2 properties that are important. Admissibility, which is essentially that the heuristic always underestimates the distance to the goal. So it's kind of optimistic. So this is good because it means that you're not delaying looking at certain node that may be successful, okay? And then the other property is monotonicity, or also continuity, consistency. And so this adds essentially to admissibility that actually you won't basically get locally misled. So the H values that you get in neighboring nodes are kind of consistent with the actual distances on the edges between these nodes, the cost. Okay. And we saw an example about where we had an admissible heuristic, but not one that was not monotonic, and how this could, cause some the search to be a little bit sidetracked. Okay, so it's easy to show that if you have monotonicity, then automatically your heuristic must also be admissible. Okay, so we can prove this by induction on the number of steps from a node to the goal node. So the base case is if you have a node that's a goal node, then h of n must be 0 by the monotonicity condition. Okay, so basically, and h star, the actual distance to the goal along the optimal path from is 0. So basically, it satisfies the admissibility condition that h is less than or equal to h star. Okay. So do you remember what h star means and all of this from last time? Okay, h of n is the value that the heuristic function returns for the node n. So it's basically how promising, what the estimate of the distance to the goal from that node. Okay, h star is the actual cost of reaching a goal node using the minimum cost path from n. Okay, so it's it's the correct distance from the goal. Monotonicity, well, this is monotonicity. So basically, the heuristic must satisfy this constraint that says basically that, if the heuristic says that in node 2, it estimates you can get to the goal for a particular value, and there's a path that goes from n1 to n2 with a particular cost. Well, at n1, since you can get to the goal by going to n2 and then taking the best path from n2 to a goal, then really this says that the estimates you give in n1 should not be more than the sum of that edge. Okay. Of course, there may be a shorter path from n1 to the goal that goes through n3. Okay, not n2. So so actually, hn1 could even be less than what's on the right-hand side here. But still, it cannot be more, because one way to go to the goal is to first go to n2 and then take the path, the best path from there. So really, this inequality should hold. And admissibility, as we said, is basically for any node, h of n must be less than or equal h star of n, and h star of n is the cost of the shortest path from n to a goal node. Okay, so it must be, optimistic. It cannot overestimate the cost of getting to the goal. Okay, so back to the proof on slide 14. For the base case, if n is a goal node, then yes, admissibility implies, monotonicity implies admissibility. Now, by induction, so suppose that you're in a node nk, and that is at most k steps, k edges, basically, from a goal node. And assume that for this one, basically, it's admissible. Okay, h of nk is less than hk. So essentially, you assume that what we want to prove holds for that node at most k step. Now we want to show that monotonicity implies admissibility for nodes that are k plus 1 step from the goal. Okay, so suppose that now we have a new node nk, which is along a shortest path from nk plus 1. Well, so take a node that's called nk plus 1 that where the number of steps to the goal is k plus 1. Suppose that nk is the next node along the shortest path from nk plus 1 to the goal. So since the heuristic is monotone, then the monotonicity must hold with respect to nk plus 1 and nk. Okay, so this holds. By the induction hypothesis, we know that h of nk is less than h star of n, less than or equal to h star of nk, because nk is no more than k steps from the goal. Okay, so this at nk the heuristic is admissible. So we can put these two together and get that basically, you know, h of nk plus 1 is less than the cost it costs to get from nk to nk plus 1 plus h star of nk, because, you know, this is greater than this. Okay, so we just, you know, by transitivity of inequality, we have this. And basically, so this is at least epsilon. Okay, it's a it's a positive real number. Okay, so and strictly greater than epsilon. So basically, you know, we know that this is, we can remove that from both from this side, and it's still greater or equal. Okay, so basically this means that with respect to h of nk plus 1, the admissibility condition is satisfied. So this means that for now, you know, by induction, for any node which is arbitrarily far from a goal state, the admissibility condition holds. And also, you know, if the goal is unreachable from a node, then h star, the cost of getting to the goal from that node is, in reality, it's infinity. So the result will trivially hold, because h has to return some value which is less than or equal to infinity. Okay, so what are the consequences of this this monotonicity property? Okay, well, one consequence is that the f values of node along a path cannot decrease. Okay, they always at least greater or equal to what they were before you took a step, before you extended the path. Okay, so as you know, expand nodes that are further and further away from the starting state, okay, the f value, which is the sum of the cost of the path to get from the actual cost to get from the starting state to the node, plus the heuristic value at that node, so the estimate of the distance to the goal, this value cannot decrease. Okay, so so basically, you know, the f value of a node ni, which is along some path. Okay, so say we have a path. So and I is a node along a certain path. We want to show that the f value is less than or equal to the f value at the next node on the path. Well, f of ni is basically equal to g of ni, which is the cost of getting from the start node to ni, okay, plus the heuristic value at ni, okay, and so basically we know that this is less than or equal to the cost of getting from start to ni plus the cost of the next edge. Actually, assuming the edges have cost at least epsilon, then this must be strictly sorry. So here we're using monotonicity because we know that this has to be less than or equal to this. Okay, so using monotonicity, we get this, and then this is really the cost of getting from the start to ni plus 1 by doing that sequence. Okay, and and this is really g of ni plus 1 plus h of ni plus 1, so that f of ni plus 1. So that's an easy proof. The second consequence is basically if you expand a node n2 after a node n1, then the f of n plus 1 is less than or equal to f of n plus 2, f of n2. Okay, so basically this is of course assuming you're using A star. Okay, so so in A star you expand node in terms of the f value. Okay, so you expand the lowest cost, the lowest f value node that's on the frontier. So how do we show that? Well, basically, suppose that n2 was on the frontier when n1 was expanded. So there immediately you have that the f of n1 must be less than or equal to f of n2, otherwise you would have expanded n2. Okay? So here this is easy. Suppose that n2 was added to the frontier after n1 was expanded. Okay? Then there must have been an ancestor of n2 that was present on the frontier when n1 was expanded. Okay? This could even be n1 itself. So basically, the cost of that node n must have been greater or equal to f of n1, otherwise n would have been expanded first. Okay, and it's still on the frontier, so you haven't expanded it. So basically now, since n is along the path to n2, and by property 1, f values always cannot decrease along a path, then we also have that f of n is less than or equal f of n2, so by transitivity f of n1 is less than or equal to n2. A third property that follows from monotonicity is if n is expanded, then every path with the lower f value has already been expanded. Okay, so we can show this by contradiction. Suppose that there's a path that goes to to ni, and then from ni to nk, And suppose this path f of nk is less than f of n. And suppose that ni is the last node that has been expanded along this path. Okay? So this is, of course, this would contradict what we're trying to show. Because here nk has not been expanded, and this path has not been looked at when we get to n, when we expand n. So now, since ni has been expanded, then ni plus 1 must be on the frontier, and this is the case while n, is expanded. So by the first property, f of nk cannot be less than f of ni plus 1. Okay. Now, since f of nk is less than f of n, so this means that it's greater than f of n by the assumption, then f of ni plus 1 is greater or equal by property 1, 2 to f of n, then so basically we have this by a, in a, and then so basically and this is less than f of n, so simply putting those two together, you get that f of n plus 1 is less than f of n. But by property 2, this would contradict property 2, because we know that along a path f of n cannot go down, and this is what you have here. Okay, so the fourth, is essentially the key property of, monotonicity when you use A star. So basically, when you're using a heuristic that is monotone, the first time A star expands a state, then it has found the minimum cost path to that state. Okay, so this follows essentially by property 3. So suppose that you have a path 1 that is the first path to a node n, and you have a particular f value for this, and then you have another path that goes to n that was found later with an f value for this path 2. So by property 3, since path 2 was found later, then the f value for path 2 cannot be less than the f value for path 1. So it follows that, and they have the same h value, so the cost, must be, the cost of path 2 cannot be less than the cost of path 1. So the first time you got to n by path 1, you had the minimum cost path to that node, or a minimum cost. There might be several paths with the same cost. Okay, so essentially this will allow us to show that A star finds the optimal path. It has the optimality property. Okay, and in a way this is a little bit surprising, because you're using this estimate of the distance to the goal. Okay, I mean it's not perfectly accurate. Okay, and so to find that, if you apply A star with an admissible heuristic, you find the optimal path to the goal guaranteed. okay, and in fact it's the first path that you find that gets to the goal, then it's a little bit surprising, okay? But essentially it follows some admissibility. Is it complete? Okay, well, basically, suppose you have a least cost path to a goal node from the start state with a particular cost. Each action has a cost of at least epsilon. So this means that there's only a finite number of nodes and paths that have a cost less than that solution path. Okay, because say E is 1 and or 0.5, and the cost of the optimal path to the goal is this one is 10. Well, this means that after you look at all the paths with no more than 20 steps, for sure you're going to run into that path. Okay, and all the paths that have cost less than this node than this particular solution path, so there's only finitely many of them. All of these paths must be explored before any path that has a cost greater than the solution path. So eventually you will find the solution path or some other one that is, as an equal, is also a path to the goal with an equal cost. What about time and space complexity? Basically, here, in the worst case, so this really depends on the heuristic function that you have, okay? But if you set the heuristic function that is extremely optimistic for every node, okay? So you say for every node, I estimate that the cost of getting to the goal from that node is 0. Okay, then basically H satisfies the monotonicity property. Okay, and it satisfies the admissibility property as well. Okay, so and in that case, basically A star becomes exactly like uniform cost search. Okay, because basically here the H of n is always 0, so f of n, which is equal to g of n plus h of n, is really just equal to g of n, and that's what uniform cost search was using. Okay, the cost of the path so far. Okay, so basically so the number of nodes that A star will expand can be basically no more than uniform cost search. In fact, if h of n is greater than 0 for some node, then the number of nodes that A star expands might be less than uniform cost search. So essentially, unless you put some more constraints on H, basically that's about as good a bound as you can get. Okay, so the time and space complexity will be essentially the same as in the worst case, the same as for uniform cost search. Yeah, optimality, basically we saw that, so it always find the optimal path to the goal if there is one. Okay, and this is the proof of the property 4 that basically when it gets to a node, it always the first time it always has the shortest path to that goal. the optimal path to that node. So if it's a goal node, then the first time you get to the goal node, you got the optimal path to a goal node. Now, what if you want to do cycle checking? Okay. Then it turns out that this is fine. Here, you keep optimality. Why? Well, because as we've shown, you know, the first time you get to a node, you found the optimal path to that node. So if you come back to that node via cycle, you can basically stop the search there, not put any successes, because, you know, this subsequent path, the second path you found to get to that node n, must be at no less expensive than the one you found first. Okay, so basically, by cutting off the search along that path, you're not, you know, you're not ignoring any faster way to get to goal node. So, so when you have monotonicity, sort of, you know, intuitively, what happens? Well, basically, with a monotone heuristic, essentially, you know, the f grows in a very sort of predictable way. Okay, so basically, just like breadth first search adds layers. Okay, so A star with f, it would add layers of different f values that are higher and higher until they include, you know, a goal node. Okay, so if you apply this to the traveling in Romania example on slide 21, so you can see that, you know, as you increase the f value, okay, from, I mean, this is based on some heuristic, okay, that we haven't given, but basically you include more and more nodes until at some point, you know, this includes Bucharest, okay, the goal node. And basically, you know, the f value here is always less than the real h star value. Okay, so when you open, you know, expand Bucharest, then you will find, and the actual f, you know, value of getting there will be no more than what f said you would have to pay to get to a goal. And so basically, a star kind of progressively moves further out, you know, in these contours of f values that are the same. Okay. Now, suppose what about when you don't have monotonicity, but you have an h which is admissible? Okay. So it turns out that, in fact, without cycle checking, all the properties that we've seen for a star still hold. Okay. So the case where h is 0 everywhere, it's sufficient to have admissibility. I mean, this is also admissible. Okay, so basically, in the worst case, the time and space complexity that we've seen, they're going to be like uniform costs, or just the same. completeness also holds. It turns out that when you have cycle checking, without cycle checking, optimality of A star still holds, okay? But now, I mean, when you have just admissibility and not monotonicity, it turns out that the F value might go down, okay, as you proceed along a path. So you need a different kind of proof that to show that first time you get to a goal state, you found the optimal path to get to a goal state. Okay, so what's the proof in this case? Well, suppose you found a goal, A star found the path to a goal state. And suppose that the cost of that path is actually strictly greater than the optimal cost to get from, the start node to some goal state. So it must be the case that there's a node on the optimal path that's still on the frontier. Okay? And so let's call this node n. Okay? So now f of n is equal to g of n plus h of n. Okay? And by admissibility, so this is less than or equal to g of n plus h star of n. This is the actual cost of getting from n to a goal node. Okay? And this is equal to the cost of the optimal path. Okay? So basically here, and by our assumption, this is less than f of g. Well, so this means that, because the f of g is greater than, f of n, then, n must have been selected to be expanded before g, the node that you went on on this path. So there's a contradiction. Okay, so even without monotonicity, if you have simply a heuristic which is admissible, so it's an optimistic heuristic, then you guarantee with A star to find the first time you get to the goal, you have found an optimal path to the goal. So now here, as I said before, so the property that we prove for heuristics that have monotonicity, if you only have admissibility, then they don't hold. So you're not guaranteed anymore to have found an optimal path to a node the first time you visit it. Okay, so if you add cycle checking, then this might not preserve optimality. But there's a simple fix to this issue. Basically, when you sort of, expand the node, now you put it from the frontier to the closed list. Okay? Now, when you do this, remember the cost of the path to get to that node that you had at that point. Okay? And now if you come to that node again, okay, then if the cost of the path to the node in the second time is less than the cost of the path that you had in the previous time when it was on the frontier and you expanded it, then you cannot cut off the search, even though it's already on the closed list. So you would put its successors on on the frontier again with the new costs. Okay, so so you need to search, starting from that node and through its successors, because you found a new path that was cheaper to get to that node. So that might be the optimal path to the goal. So basically in the search, you no longer have, strictly increasing, or non-decreasing F value. Okay, so basically, A star has very nice properties. Now, one thing to observe, though, is that like breadth first search, A star does have an issue with the amount of space, the space complexity. As we saw in the worst case, it's like uniform cost search, which has, requires an exponential amount of memory, exponential basically in the distance to the goal, okay, or the number of edges to the goal. So in fact, there's a way to, in uninformed search, we found that there was a better way to do things with iterative deepening. Okay, which is essentially iteratively doing depth first search. Well, we can do a similar thing for A star. So we can do iterative deepening A star. Basically, you put the newly expanded node in the front of the frontier, and you cut off. You have a bound on the search. Okay, and so now, what you want to do is basically the bound is going to be an F value, and basically, so you keep going down the branch until you hit the bound on the F value. Okay, at that point you don't have the successor, and you backtrack and try different, paths. So, however, here you should remember when you cut off the search, okay, whether or not, if you explore the whole space, then, you can give up, basically. And if you don't find a path to a goal. So you remember, that whether you cut off the search, and also the smallest F value that was basically discarded in the current round, okay? Because at the next round, you need to increase the bound to this F value. Okay, so this is going to give you all, allow you to explore paths that go up to this new F value. Okay, and there might be a path to the goal in that class. Okay, so now. So, of course, this redoes the search, for the next F value. So there may be many iterations of the search, like we saw in, when we discussed iterative deepening, and the cost of edges was different. Was not a constant cost. So, so you may, but in terms of space, this is great. In terms of time, it might not be so great, but, yeah. Another thing to point out, of course, is, this is if you want the optimal path, okay? If you're willing to be close to the optimal path, but not necessarily have the actual optimal path. So, for example, if you want to find the best route to get to somewhere, but you don't necessarily get the want the absolute best route, maybe a route that is within 10% of the best route, then here you could increase the bound by, larger amount, okay? And so then you do fewer iterations, but so the running time is less, but you get something which is close to an optimal solution. Okay? Okay, so this was essentially the techniques for doing heuristic search. And you will explore this in the assignment. So you have to do things like use A star, use iterative deepening A star, and so on. One big question that's left is basically how do you get the heuristic? Okay, so heuristics incorporate some knowledge of how to solve problem, which is specific to the problem. Okay, so it's not obvious how you can, other than gathering a lot of experts, it's not clear how you come up with the heuristic. Say for example, you want to do a timetable for exam for York University. Okay, so you want to find an optimal schedule, okay, or close to optimal schedule. So it's not obvious, and you could ask expert, how do you come up with good estimates for how close you are to having an optimal, on the path to getting an optimal schedule by scheduling individual exams. Or if you have a path planning problem, you want to send your robot to a particular location, kind of on a graph, then, again, there might be a lot of tips, techniques that you can come up to get estimates for the cost of particular, of getting from various points in the space to the goal destination. So, so here we're going to look at, general techniques for building heuristic. And one that's very useful is basically to take a problem that you have and simplify it in some way. Relax the constraints that apply to moves in the problem. Okay? So if you do that, then the problem may become much easier to solve. Okay? And so now you can calculate the cost of the solution in the simpler version of the problem and use this as your estimate for the cost of reaching a solution in the full problem. Okay? So to take an example, suppose that you have the 8 puzzle. So remember, this is the problem where you have tiles and they may be randomly placed with one, and you have to slide the tiles until you reach the goal configuration. Okay. So in the 8 puzzle, the constraints on the move is that you can move a tile from a position A to position B if the two positions are adjacent. So this is a move to the left or the right or up or down. Okay, just one step. And then the other constraint is that the square you're moving to is currently blank. Okay, you cannot simply, if there's another tile there, you cannot move there. Okay, so this makes the problem kind of complicated to solve. Okay, because you to get from the start state to the goal state, you have to move a lot of tiles from, there are not a lot of tiles that are not at the right place, and you got to find a way to move them around to get to that, final configuration, that goal configuration. But now consider different ways of relaxing those constraints, making the problem easier. Okay? Well, one would be to say you could forget about the position you move a tile to being blank. Okay? Maybe you don't care. Okay? So this kind of would imagine that you can kind of stack up tiles in a place. Okay? You can have more than one tile in one place. A second way you can relax it would be to say that you can move from a tile from position A to B as long as B is blank. Doesn't have to be next to A. Okay? So you can basically have tiles that jump. Okay? Jump to the blank spot. Okay? And a third way would be to ignore both. Okay? So when you ignore both, basically you say, well, tile 1 has to go to this other position, tile 2 has to go to this other position. So in at most 8 moves, you're going to have everybody in the right place. Okay? So here you made the problem very, very easy. Okay? So if you choose number 3, this simplification of the problem, essentially you're counting the number of tiles that are in the wrong place. This is called the misplaced tiles heuristic for the puzzle. Okay, the eight puzzle. Okay, so here to solve the puzzle with this relaxed version, you only need to move each tile into its final position. The number of moves you need is the number of tiles which are not in their correct position. Now, clearly this is admissible, okay, with respect to the original problem. So the number of misplaced tiles is clearly less than or equal the number of moves that you need to do in the real problem. Okay? Generally, it's much less, but so this means that really number of misplaced tile is an easy way to estimate, to get an optimistic estimate of the distance to the goal in the original problem. Okay. If you use the first relaxation, where basically you ignore the need to move only to a blank. Okay, so essentially this means that the moves now are moving up by 1 or left by 1, right by 1, and so on. Okay, so essentially this means that to solve this version of the puzzle, so it's fairly easy, because if you have a tile here that needs to go, say, here, then you know that you need to go do 1, 2, 3 moves. Okay? So essentially, to move that tile to the right place, you use essentially the distance of the Manhattan path. Okay? Manhattan path is, this idea that, you have to navigate move around in a city like Manhattan, where the roads are all on the grid. Okay? So there's no diagonal roads or anything like that. So basically, to solve this version of the problem where you ignore the blank, for every tile that is not in the right place, you calculate the path, the number of step that you would need to get it to the right place. And you take the sum of these for all the tiles. Okay, so essentially, so the number of move is the sum over all the tiles for the number of vertical and horizontal slide that they need to be moved into the right place. Clearly, again, this heuristic value, which is the sum of the Manhattan distances for all the tiles, underestimates the cost of the true solution, the number of moves you would have to do to solve the puzzle if you had to worry about the blank. Okay? So, if you basically, in the real case, if you want to move this guy here, you may have to flip this to put the blank there. Okay, so you might need to do extra moves. So it's admissible. So the point of this technique where you find a relaxed version of the problem, you simplify some of the constraints on solution. Basically, the optimal cost of solving the relaxed problem gives you a heuristic. So from a given configuration, gives you a heuristic. This cost can be used as a heuristic with respect to the original problem, and it's always an admissible heuristic because it underestimates So basically here, to prove this, you can show that, whenever you have an optimal solution in the original problem, then it must be at least as expensive as the optimal solution for the relaxed problem. So it's a kind of lower bound on the... and if you run some experiments, you can see that actually the value of these heuristics is huge. Okay, so here we're comparing iterative deepening search, which doesn't use any heuristic, but it's a quite efficient. We saw it kind of the most efficient uninformed search method. Okay, so if you apply it to 8 puzzle example, or then if you at depth 10 it might expand 47,000 nodes. At depth 14 it might expand 3 million something nodes. Assuming the solution is there, okay? Well, if you use A star with the misplaced tile heuristic, the number of nodes it expands is much, much less, okay? It's here it's 539 compared to 3 million. And so this means you cannot go very deep, but with the heuristics you can go very deep. You can look at paths that are quite long. Okay, and that these paths are pretty good because really they must be less than the optimal path to the goal, because it's admissible. If you use Manhattan distance heuristics, it's even better. Okay, generally, here for 24 paths of length 24, okay, or depth 24, you only have 1,600 compared to some huge number for iterative deepening star. And notice that Manhattan is always better than misplaced tile, because essentially, so misplaced tile, you've simplified the problem so much that you get a very coarse, too optimistic value. With Manhattan, you consider the number of steps you need to do, so the H value is always higher in Manhattan than in misplaced tile, and this gives you a better estimate of the distance to the goal. So, in fact, there's a way to try to show that a heuristic, say H2, is always better than H1, always expand fewer nodes than another heuristic H1. Basically, if H2 of n is always less than or equal to H1 of n for all nodes, then we say that H2 dominates, H1. And as long as they're both admissible, then this means that H2 gives you more information, okay? It's less optimistic, but it's closer to reality, okay? So, so basically, if you have many admissible heuristics, you want to use one that's the highest, okay? Because it's still less than H star, but it gives you a better estimate of the true distance. Okay. Now, another technique that can be used is what's called pattern databases. So this is a bit like endgames in chess. Okay. Basically, you look at configuration where there's only a few, pieces left on the board, and so you can actually calculate by, kind of brute force to find what's the optimal sequence of moves to win the game. Okay? So here, basically, you look at some partial specification of the problem, and you compute an optimal solution given this. Okay, so basically, an example would be in the 15 puzzle, okay, which is like the 4x4 version. So you can define a subproblem where the only thing that matters is getting the lower row and the right column in the right place. Okay? The other squares don't matter. Or another one is this one, where you have to get the... so this is the fringe, subproblem. And, sorry, the corner subproblem. This is the fringe subproblem, where you need to get the last two rows correct. Okay? So here, you made the problem easier. You just want to get those things. So you have more goal states. Okay? And so it becomes feasible for any state to find the shortest path to a goal state of that kind, okay, or of that kind, okay, because you don't care about the other. You made the problem much simpler. So if you can do this, then the optimal solution of this problem, of course, you need to solve this problem to solve the whole problem. So it gives you a lower bound on the cost of solving the whole problem. Okay, so for any state, the number of moves required to get these tails into place is a lower bound on the cost of getting to the real goal, which is to get all the tiles in the right place from the node. So basically, you can put, all of these configuration with the associated. So you can have many of these configuration, and you can put them in a database with the number of moves required for getting to the current state or to any state to that configuration in the database. So now basically you can, whenever you're in a state, you can look at all of these subproblems in the database, these patterns, and the one with the largest number of moves, you can use this as your heuristic. Okay, so basically, one way is that for the fringe pattern, you have a whole database. So for every configuration, the cost of solving the fringe goal is so and so. Okay, you can do another one for the corner. Okay, and so each of those is, if you use this one, you're going to get 345-fold decrease in the search tree size, the number of nodes you expand, and similarly for corner. Now, here you can only use one database, okay, at a time. So you use the one that gives you the highest estimate because they're all admissible, okay, but you cannot combine them. Another thing you can do is to look for disjoint database, disjoint pattern, okay. So because here, there was some overlap between the tiles here and the tiles here. Okay? So you cannot just say it would take me, 10 moves to solve this and 12 moves to solve that, so I have to solve both, so my estimate is 22. You cannot add them. Okay? Because there's some overlap, so the move you need to solve this might be the same as these. Okay? However, if we had, this fringe and then another one which is, say this part, then there would be no overlap. So then you can just add the number of moves. Okay? So these would be disjoint problems. So you can also try to do that. Find patterns which correspond or disjoint, and then you can just add the heuristic for each of them to get a better heuristic rather than simply taking the dominant heuristic. Okay, so this is pretty much all I'm going to say about heuristic search. I just want to close on a final topic. Okay, so and this is basically about local search. So in the algorithm we've seen so far, we want to find the path to the goal, and we're interested in what the sequence of moves you need to do. Okay? But there are problems where we don't care really about the path. All we care is the solution. Okay? So one example is 8 queens. So you have a chessboard and you want to know where you can place the queens so that none of them threaten each other. Okay? None of them can eat the other queen. Or another example is exam scheduling. So you don't care what order you set the exam. What matters is that you've got your schedule at the end where you know which courses are going to have exams in which room on what day. Okay? Doesn't matter how you got there. Or integrated circuit design, or, lots of problems are of this form. So one approach that can be used in this case is what's called local search. Okay? And local search generally, the simple version is there's one current state, and basically at each iteration you move to a neighbor. Okay? So basically you're searching locally to try to find the goal state. Okay? You start in some starting state, and then you move around. Okay? You just care about finding a goal state. But of course in a space where there's lots of variables. Now, basically, generally here, you need some function that tells you when you reach a goal state. And in many cases, there's a function that tells you how good, a state is. Okay? That's the objective function. And really, what you might have is an optimization problem. So you're trying to find the best schedule. Okay? Or for the 8 queen, you could say, well, the objective function is to have no queen threaten each other. Maybe the number of queens that threaten each other is, kind of the value of the objective function. So there, if you have this kind of problem, then you can try simple algorithms, like essentially hill climbing, or sometimes this is called gradient descent. Okay? Basically, you want to try to move from the current state to a neighbor in a greedy way. So you want to get the best increase in the value of the objective function for the node you go to. So essentially here you can think of the space as being, a bunch of hills and valleys. Okay? Mountains and pits. Okay? And you want to get to the top of the highest mountain. This is the maximum of the objective function. Okay? So hill climbing tells you keep going up. Okay? Of course, with hill climbing, this is very, very simple greedy approach. Then you may become stuck in the local maximum. Okay? You reach the top of a little hill. Okay? And of course, there's many bigger mountains, but you're never going to get there, because hill climbing says only move to a neighbor that's higher. Move to the highest neighbor. Okay, so you would keep going back and forth near the top of that little hill. Okay, because hill climbing does not allow you to go all the way down, then to go to the mountain that's further down. Okay. Now, so to avoid this problem of getting stuck in a local maximum, one thing you can do is to add some random moves. Okay? Essentially what you want to do is sometimes you want to just shake the position of so that you get out of your local maximum and start searching again. Hopefully, if you do this enough times, you will find the global maximum. So the different local search algorithms are basically approaches to try to do this. So one approach is called simulated annealing, And here, basically, with a certain probability, it's going to make a random move. And then 1 minus that, it's going to be greedy, do hill climbing. Okay, take the best move. With simulated annealing, initially the probability of making random moves is quite high. Okay, and over time you cut it down. Okay, until at the end it's pure hill climbing. Okay, so basically, instead of always making the best move, make a random move, and if it improves the situation, always accept. Otherwise, accept it with a certain probability, and you decrease the probability of accepting lowering move over time. Okay, this has been, imagine it's a little bit similar to what happens when you cool a metal. Okay, you have some hot metal and you slowly cool it, and then the metal will stabilize in a good state. Another thing you can do is basically do a parallel version of this. So instead of having just one current state as in hill climbing, you can have k-state, a population of current state. Okay, and then at each iteration you choose the k best neighbor. Okay, so essentially you have multiple search threads going on at the same time, and they share information. So the beam search is really like local search, but with a population of state, and there's a version which is stochastic, like simulated annealing, where you're working with population. And essentially, you may have heard of genetic algorithms. So genetic algorithms, they try to do search by using ideas from genetics. Okay, it's kind of a special case of stochastic local beam search. Okay, you have a population of individuals. At every step, you do mutation. Okay, and you eliminate the worst children. You keep the best children, and you keep going that way. And you hope that eventually, you will have some optimal individuals in your population. Okay. One difference between genetic algorithm and stochastic local beam search is that how it generates the new generation. Okay, the new node. So here, genetic algorithm, they tend to basically analyze the state into a set of features or a set of variables. Okay, and to generate the children, basically you will take some components of the state and swap them with some other individual. So basically, usually you choose two parents and you cut the gene sort of in the middle, and you use one from a parent and the other part from the other parent, or some region from one parent, some other region for another parent. Okay, so and what this does is it kind of gives the search becomes kind of hierarchical. Okay, because you're trying to combine chunks of solution to get the optimal state, the optimal setting of all the features or the variable. Okay, so of course here the design of the state representation becomes very important. So this has been quite popular. Okay, so this is basically, let's take a little break now, and if I'm going to bring out the test if you want to pick up your test.